Hey guys, welcome to your chemistry lesson for today on electrolysis. So, where we left off yesterday was you guys looking at electrolysis on your own of aluminum oxide and also learning the reactivity series. So, we're going to focus on that today and learning how we can use it. Specifically, though, we're going to look at the electrolysis of aluminum oxide, which is called bauxite, to make aluminum, which is going to be very important to you in the coming days. So first off, why are we even learning about something called electrolysis? Well, most metals are not found pure in their natural state. They're actually found as compounds. And these compounds we refer to as ores. So these metals, in order to be useful, we have to extract those from their ores so that they can actually be made useful. So this method of extraction absolutely depends on the reactivity of the metal being extracted. And that's where our reactivity series actually comes into play. So any metal that is above carbon in the reactivity series can be extracted using electrolysis. So that means anything from aluminum up to potassium, we have to extract with electrolysis because these metals are too reactive to be found naturally. So again, they're found in what we call ores, and we extract them by electrolysis to make them useful. So in other words, for us to get pure aluminum or pure magnesium or pure calcium. All right. With electrolysis, let's just do a little refresher to make sure we remember what that is, because you do need to know the definition. So electrolysis is the breakdown of an ionic compound. Remember, ionic compounds contain both a metal and a nonmetal. And these ionic compounds have to either be molten, which means we just heat them to an incredibly high temperature to liquefy them, or they can be in an aqueous solution, which means dissolved in water. And we do this by using electricity. Electrolysis, though, is really, really expensive, but it's also the only way to extract reactive metals. So here are the metals that you all memorized for me. And they increase from platinum up to potassium being our most reactive. I also had you memorize the nonmetal series, and we're going to talk about those, but it's going to be just a little bit later. So first off, let's look at just the general order of reactivity. If you've got your periodic table, you'll notice that we have our metals mainly to the left-hand side and our nonmetals mainly to the right-hand side. And they have a common trend depending on if you're talking about metals or nonmetals. Our metals, which are anything after this zigzag right here, they increase in reactivity to the left and down. So that means my most reactive metal in this periodic table is francium. Anything to the left is going to be more reactive than anything to the right. So an example, if we were talking about potassium as compared to magnesium, even though magnesium is further up, it's going to be less reactive than potassium because potassium is further to the left. So anything to the left is more reactive than something to the right. This is useful because a lot of times on the Cambridge exams, they'll give you something like, say, barium. Barium's not on our list, but they might say, well, which one's more reactive, calcium or barium? What would you expect is what they would say. Well, since barium is further down than calcium, that means I could predict that barium is more reactive than calcium, which means it would react more explosively. Now let's look at our nonmetals. Our nonmetals have a trend, but that's directly opposite that of my metals. My nonmetals increase to the right and up. And notice I'm going to exclude group number 8 because group number 8 are our noble gases. And if you recall, noble gases are unreactive. So that's why they do not get put in with the series. So we're looking at anything that is in this green area. All right, so my most reactive nonmetal then would be this fluorine, because it is the furthest to the right and the furthest up. In comparison to, say, nitrogen, fluorine is still going to be the most reactive because it is further to the right. If I were to compare, say, phosphorus to oxygen, well, oxygen would be more reactive because it is further to the right. If we look at just our halogens, let's look at bromine. Bromine is below chlorine and fluorine. That means that it's less reactive than both of those. So chlorine would be more reactive than bromine, for example. This whole idea is going to be so important for the next couple of weeks of our lessons. So be sure you understand how that trend works. Remember, our metals increase in reactivity to the left and down, and our nonmetals increase in reactivity to the right and up. And something else you should understand is that you're never going to compare metals to nonmetals. So you can't say like sodium is more reactive than fluorine, because those are two different things. That would be like comparing apples to oranges. So that's not ever going to happen. You'll always compare metals to metals and nonmetals to nonmetals. All right, let's move on. So we were looking at aluminum specifically yesterday. The ore that aluminum is taken from is called bauxite. And yes, you do need to know that bauxite is what it's called. The chemical name for bauxite is aluminum oxide. And you'll notice the formula here is Al2O3. Electrolysis is going to actually separate this aluminum from that oxygen. And when this takes place, this aluminum that it's going to take is going to lose oxygen. Anytime a substance loses oxygen, it's called reduction. All right? So our word equation, if we wanted to look at that, which we do, so we start with aluminum oxide here. And remember, that's our formula, Al2O3. So we start with Al2O3, and then this little box should actually be an arrow, and we produce aluminum and oxygen. Now, what you're going to notice that just happened, see that 2 right there? I bet you guys would not have thought about putting a 2 there because I've not taught you to do so. Let me tell you about some compounds or some molecules that are a little different, and you absolutely need to know. Make a note of this. All right, let me erase some of this malarkey that I've got on my screen here so you can see everything. 1 second. All right, perfect. Well, it's perfect as it can be. When there are some molecules by themselves, they are paired up. So if we have, say, for instance, nitrogen all by itself, it can't just be nitrogen with an N. It's actually going to be N2. The same goes for oxygen, fluorine, chlorine, bromine, and iodine, and hydrogen. These, when they are by themselves, come in pairs, and they're called diatomic molecules. That's important to you because if you're making an equation, and you will be making many of them, if they are written by themselves, like if you just see the word nitrogen in an equation, or you just see the word oxygen or hydrogen, it's not just going to be the symbol. It'll be the symbol followed by 2, meaning you've got to have 2 atoms of that specific element to make that molecule. So if you had just hydrogen, it would be H2. If you had just nitrogen, it would be N2. Just oxygen, O2. Just fluorine would be F2. Chlorine would be Cl2. Bromine would be Br2. Iodine would be I2. So anytime you see any of these and you just see the element name in an equation, you've got to follow it by the number 2 because that means you've got 2 atoms of each one of those to make that molecule. That's just how it is. An easy way to remember it is going to be anything in group number 7, so all of group 7. And then also your oxygen, nitrogen, and hydrogen. You got to know that. All right. So back to looking at this. So that's where that O2 came from. The other thing that's necessary is to know what state of matter these things are in. So anytime you have an or, an ionic compound in general, unless it's dissolved in water, it's going to be solid. So you would have a little S in your equation at the bottom. And since we're making aluminum, aluminum is a metal, and metals are solid except for mercury. So aluminum over here would have a little S down below it. And now oxygen, think about what oxygen is. We breathe oxygen every day, right? I hope we do. That's a gas. So to show that it is a gas, it gets the symbol G. It's about to get the symbol G. G. So just so you know these symbols and equations, because we're going to be looking at them for a while. An S always stands for solid, an L for liquid, a G for gas, and then if your ionic substance is said to be aqueous, then it is dissolved in water, and that means it would have an AQ. And these are always subscripted in parentheses. So that's what you're seeing right here. Now, we haven't looked at balancing equations yet, but we are going to touch on that today. So let's run on through this. And again, this, we started with aluminum oxide. That's our bauxite. We broke it down or decomposed it into aluminum and oxygen. And since that aluminum here lost its oxygen, that is called reduction. When you lose oxygen, it's reduction. If you gain oxygen, it is oxidation. Write that down. So reduction, I'm going to jot this down for you, equals loss of oxygen by a compound. The opposite of that, which you need to know, is called oxidation. Oxidation, just as it sounds, is the gaining of oxygen by an element or compound. We're going to look more at that today. So one way of looking at oxidation and reduction is losing oxygen. Oxidation is gaining oxygen. All right, moving right along here. Let's do just a very brief review over how we even get these ionic substances into simpler ones. Let's recall, ionic substances are made up of charged particles called ions. Remember what an ion is. You had to write this out at one time. An ion is an atom that has either gained or lost electrons. So that means it either carries a positive or negative charge, which is shown after its formula. So ions with a positive charge have lost electrons, and ions that have gained electrons are negatively charged. Let's make sure we remember which ones are what. Remember metals. So that's anything in group numbers 1, 2, or 3, and all the transition metals. They are always going to lose electrons, which means they're always going to be positive when they're ions. Nonmetals, they always gain electrons. So that means they're always going to be the negative ion within your substance. And remember, these ions have specific names. And if you don't remember that, you need to write it down. Negative ions are always called anions. positive ions are always called cation, not cations, cations. All right. So with electrolysis, we have to either dissolve one of our substances in water or melt it. So when we dissolve or melt, give me 1 second here. When we dissolve or melt, this allows these ions to move freely. That is so incredibly important. Write that down. The reason that ionic substances can conduct electricity in the molten or aqueous state is because their ions are free to move. I'm going to say that again because you need to know that. The reason that ionic substances can carry a charge, in other words, conduct electricity in the aqueous or molten state, is because their ions are free to move. All right, so just an example over here to the side, you see an aluminum atom, and this specific electronic structure is showing the full thing. So aluminum is atomic number 13, so it's got a full 13 electrons. But remember, when it comes to bonding and reactivity, it all has to do with the valence electrons, which are those outermost electrons. And aluminum has 3 of those. And remember, you can know the number of valence electrons by looking at the group number. All right, so since aluminum is a metal and only has 3 valence electrons, when it forms an ion, it becomes positively charged by 3 because it's going to lose those outer 3 electrons. So what is left is a full outer shell, as you can see right there. And that's the goal. So during electrolysis, what happens is the ions that are part of our ionic compound break apart into their independent ions. Now, once that substance is split up, so once my ionic compound is split up, that is called the electrolyte. This electrolyte will have both your positive metal ions and your negative non-metal ions. Just to refresh, remember the positive ions are called cations, and our negative ions are called anions. So my electrolyte, which in this picture is what that brown stuff is, it has both my positive and negative ions in it, my cations and my anions. So what happens to these ions during electrolysis? That's the whole thing here. First, let's label our diagram here so that you know what I'm talking about. So remember my positive electrode, remember these things that are in my electrolyte are called my electrodes. My positive one, do y'all remember what it's called? Positive is my anode. The negative electrode is my cathode. Now, in case you think you're going to forget which one is positive and negative, in previous notes before we had our break, I had you write down the acronym PANIC, which stood for positive anode, negative is cathode. So that tells you your anode is positive and your cathode is negative. But now keep in mind, opposites attract. So whenever we perform electrolysis, the ions that are going to be attracted to them will have the opposite charge. So, like we're seeing right here, my negative ions are going to move to my positive electrode. So again, that's my anode. And at that anode, it's going to lose electrons. And that is called oxidation. Now, you already have one definition of oxidation, which is the gaining of oxygen. So this is another definition of it, both of which you need to know. Oxidation is also losing electrons. All right, now at my negative cathode, so here's my little cathode, it's negative. My positive ions are going to move toward that negative cathode because opposites attract. So you'll see here my positive ions are all moving toward my negative cathode. And in this little bubble, you see that my negative anions are moving towards my positive anode. See how that works? My anions go to my anode. My cations go to my cathode. So now at my cathode, those positive ions, they're going to gain electrons, and that's the process of reduction. So now you have two definitions of reduction. Reduction is either the loss of oxygen or the gaining of electrons. I know that sounds confusing. We're going to work with it though. There's an easy way to remember what happens during oxidation and reduction. And I had you write this down before I break too. Oil rig. Oxidation is loss of electrons. Reduction is the gaining of electrons. So when we have these oxidation and reduction reactions, they're cumulatively called redox reactions. So these are the first reactions that we're talking about this year, redox reactions. Just coming from the word oxidation and reduction being smushed together. When we have these redox reactions, we create half equations. Meaning we're going to take our anions and create a reaction and our cations and create reactions or equations for them. So let's take an example here. Here they're showing me magnesium plus oxygen gives me magnesium oxide. So your first thought could be, if I look at my equation in symbols, magnesium plus oxygen gives me magnesium oxide. Our first definition is relevant. Magnesium is gaining, see my magnesium here? It is gaining oxygen. And remember, the gaining of oxygen is called oxidation. So here, magnesium is going through oxidation. Now, it's not so easy to see that my oxygen is going through reduction until we split them apart. And that's where you have to lean on that second definition of reduction being the gaining of electrons. So all you do is split up what you got going on. So here, I've got magnesium first. So I'm going to take magnesium. You'll see it down here. And then this should be an arrow. Produces magnesium 2 plus ions, and it gains 2 electrons. So the reason I know that, look at magnesium oxide over here. You've got to think of the ions that compose magnesium oxide. We have magnesium with a 2 plus charge and oxide with a 2 minus charge. You get those from the periodic table. So when we're writing our half equations, we're looking at the ions they become. So we started with magnesium with no charge because it is in its pure form. If something is pure and is not in a compound, it has no charge. It is stable. So that's why I have magnesium written alone. And then we're producing magnesium ions, and magnesium ions always have that 2 plus charge. And that's happening because when magnesium goes to my negative cathode, then it gains electrons. For it to become solid magnesium, though, it has to gain 2 electrons. The way I know that is, in order to become stable, this charge has to disappear. But the only way that it can disappear is if it is equal to 0. The way that happens is by electrons, because remember, each electron has a negative charge. So if I have a positive 2 and I add to that 2 electrons, which are negative, I have an overall charge of 0. With this reduction one, remember we started with the word oxygen. So we had to put that 2 next to it because oxygen is one of those diatomic molecules. So here we're starting with oxygen because that's what's on in my equation right there. And what we're producing over here is that oxide ion. So this box here should be an arrow. Initially, we would have this right here. I want you to see our beginning. But in order for this equation to work, you have to balance it. So when we're balancing equations, you have to have the same number of atoms on each side of that reaction. So in order for me to make this work, you have to put a 2 out front there. It's because I have 2 oxygens over here. I have to have 2 on this side. Now, we just said that oxygen is going through reduction. So it's gaining electrons, and I know how many it gains based off of the overall charge on my anion. So I'm looking right here. Each oxide ion has a 2 negative charge, and that number out front, that 2, that tells you have 2 of those. So I have to say that 2 times my charge of 2, and that would give me an overall charge of -4. So I have to have my sides equal, and the only way you can equal out when it comes to charges is by adding electrons. You can never take away. So that's why over on this left-hand side of my equation, I added 4 electrons, because then my overall charge over here is going to be a -4. Because remember, anything that's in its elemental state, which is its pure state, has a 0 charge. So this oxygen there, it doesn't have a charge. It's 0. So now this side is -4 and this side is -4. All right, we're going to work with it some more. I know that's challenging. All right, so let's just look a little more closely at aluminum by itself before we look further at those different redox reactions. Aluminum is highly tested on this Cambridge exam, so that's why we were taking a specific amount of time to look at just aluminum, and then we're going to look at the individual redox reactions that will also be important to you. So aluminum is one of our most useful metals in the whole wide world, and that's because we use it for cans, aluminum foil, airplanes. We use it so much. So when we want it, we have to use electrolysis to get the aluminum from its ore. Remember, that ore is called bauxite. So we want to know, why is it not possible to extract aluminum by heating its ore with carbon? Well, aluminum ore, bauxite, is more reactive than carbon. And when an element is more reactive than carbon on the reactivity series, that is when we can use carbon to help, or we can't use carbon to separate it. I'm sorry, you hear my phone ringing. Just ignore it. All right, aluminum ore is more reactive than carbon, and it has a super high melting point of 2050 degrees Celsius. In electrolysis, this ore is going to be dissolved in a compound called cryolite. And yes, you need to memorize the formula for cryolite, Na3Al(F)6. Now, what this does is it lowers the melting point to 1,000 degrees Celsius. When you lower that temperature, that means it's going to take less electricity to perform electrolysis, which is more cost effective. So that's why we want to lower the temperature. So what processes occur at the electrodes during this electrolysis of aluminum oxide? Let's look. So at the negative electrode, so remember our negative electrode is called our what? Cathode. So at our cathode, aluminum ion, so the aluminum from here, right? It's attracted to my negative cathode, and at that point it gains 3 electrons. It wants to gain those 3 electrons because what we're trying to produce is solid aluminum, which means the metal aluminum. All right. At the positive electrode, remember our positive electrode is called the anode. That's where our oxide ion goes from. So here's coming from our aluminum oxide. This is our oxide ion, and this should be an arrow. And what we're going to produce there is oxygen gas, O2. All right, so the first thing we did before adding electrons, you had to balance your equation by putting a little 2 out front here. So I have 2 oxygens and I have 2 oxygens. And now that oxygen or the oxide ion is going to lose electrons at that positive electrode. It's going to lose 4 of them. That will make the overall sides equal. We'd have -4 on this side, -4 on this side. So aluminum, since it gained electrons, that's called reduction. My oxide ion, since it lost electrons, is called oxidation. So my overall equation for the extraction of aluminum by electrolysis is aluminum oxide, so this is the Al2O3. These should be arrows. Produces aluminum and oxygen. So aluminum, Al, and oxygen, O2. Now let's look at the state symbols. We have an L here, an L here, and a G here. And that's because, remember, when you looked at this yesterday, within my cell here, that aluminum oxide is molten, which means it is liquid. So that's why the aluminum oxide has an L over here, because it is molten. We had to liquefy it by heating it really, really hot. And then when it's attracted to my negative cathode, it's still in liquid form because it's becoming aluminum metal, but it's still in the molten form because it's still in that hot bath of substance. But then the oxygen is being reacted to the positive electrode, and it's losing those electrons. And when it does that, it just becomes oxygen. Like we breathe, oxygen can only be in gaseous form. And what happens when that oxygen is being attracted to those carbon anodes, it's actually producing carbon dioxide because the carbon dissolves away to bond to that oxygen, creating carbon dioxide gas. And that's why these electrodes, they start wearing away over time and they have to be replaced. And yes, you need to know that. So the extraction of aluminum from its ore by electrolysis requires a significant amount of energy in the form of expensive electricity and to complete all the stages. So the energy is first needed to melt it, to split up our compound. To reduce that cost at the aluminum extraction plants, they're often located near cheap sources of electricity, like hydroelectric dams, so that it doesn't cost as much. All right, that's where we're going to end for today. Make sure you've done all your notes and make sure you have submitted those. See you tomorrow. Bye now.